In lecture 23 of Symmetries, Particles and Fields, we're going to construct the unitary irreducible representations of the Poincare group. As we shall see, these necessarily form into two classes, massless and massive ones. Massive representations are a bit easier to handle, so we'll do those first, and then we'll go to the massless one case. So to construct our induced representations, we remember what our group is. So G is the proper orthogonal Lorentz group in a semi-direct product with four-dimensional translations in four coordinates. And we need to pick a subgroup. And we do that by picking a particular four momentum. And I'm going to call that P dot mu. It's just so the dot is just a label for a particular four momentum. It does not in particular indicate any derivatives. So we need to define our little group. So we start by defining our little group at this point. So this is the set of all Lorentz transformations where the Lorentz transformation leaves P dot invariant. So in other words, the little group of SO1, 3. We form a representation space by the set of all of these P dots. A set of all quantum states that are labeled by P dot. So we're going to call representation space V P dot by set of all states with which are labeled by P dot. And so now I'm going to use anti-hermitian operators. And so the operator big P mu acting on our state gives us back IP dot mu acting on the state. And okay, so V P dot defines a representation space for our little group. For H is G P dot direct product with four-dimensional translations. Okay, so the cosets are labeled by the transformation that takes us from P dot to P mu. So the cosets are labeled by the Lorentz transformation. So I'm going to shorten this because I have to write it quite a few times. I'm going to shorten it to NLT. That transforms from P dot mu to P mu. In other words, we're going to call this L, so it'll be a function of P. Where it's defined in the following way. So P mu is P dot times L of P to the -1, the muth component of that. Or equivalent, another way of writing this P mu is equal to L of P mu nu P dot nu. And we're going to call this equation 9.2. And this is for all, remember, it's for all P mu such that P mu squared is equal to P dot squared. So that's from the last lecture, that stipulation. Now notice that L is a Lorentz transformation, so it satisfies the matrix equation like that, where eta is the Minkowski metric. So this equation implies that L transposed n to the minus 1 is I, or in other words, L to the minus 1 is equal to eta L to the minus 1 eta to the minus 1. Okay, so this means that P mu, which is P dot nu L to the minus 1 nu mu, well, we can substitute in for L to the minus 1 now, and we get P nu eta L transposed eta to the minus 1 nu mu. So if we write this out in components, this is P dot nu eta nu rho L transposed rho sigma sigma eta sigma mu, and which is, so I can use this eta to raise the index on the P dot. And all this transpose does, if I take transpose away, I must switch the ordering of the indices. So this is L sigma rho, P dot rho eta sigma mu. So in other words, we have that P mu is L of P mu nu P dot of nu, P dot nu. So we need to define some basis. So following the method of induced reps, a representation space of G is defined in terms of a basis that basis are these states P, which is some unitary operator that's going to now depend on this L of P acting on P dot. And so this is in the representation space of P for all P dot in VP dot. Okay, so if we, in other words, if we vary, we have a basis of these P dots, and if we vary those, then we can generate the general space for P by using this unitary operator with the encoding the Lorentz transformation first. So in other words, we can Lorentz transform from P dot to P. So finding a representation of the Poincare group then just requires a determination of u lambda of P for arbitrary lambda. So this unitary operator acting on our states must be a linear combination of all states in the vector space. So let's call that P prime set, where P prime is related to P by Lorentz transformation. Let's call that lambda. So since P prime mu is Lorentz of P, this L of P prime times P dot nu, so I should put the indices in, and we've got mu and a nu there and a nu there. So this one's going to be 9.4. We can show that P dot mu is equal to L of P prime to the -1 lambda L of P mu nu times P dot nu. Now we can see this because this combination here is P mu by 9.2. This combination here is then P prime mu from the definition of lambda, which is here. And the whole thing then is L of P prime to the -1 P prime mu. This is equal to P dot mu from 9.4. So what we've got is that this thing in brackets leaves P dot nu invariant, and we found our member of the little group. In other words, this L of lambda P to the -1 lambda L of P, which we're going to call the whole thing is Lorentz transformation because it's the product of Lorentz transformation. We're going to call this lambda P dot. This is the member of the little group. And of course, it's in our space, our vector space VP. So this one I'm going to call 9.5. Now, the representation of this in terms of unitary operators requires that U of lambda acting on P is U of L of lambda P. So I've just multiplied on the left by an L of lambda P here, times U of lambda P dot acting on P dot. So this is in VP, of course, as well, 9.6. So all we've done is multiplied by the Lorentz transformation. So the proof of this is that the right-hand side of 9.6 is U of L lambda P, U of L lambda P to the -1 lambda L P acting on P dot, which is equal to U of lambda P. So the unitary operators, the unitary operator of a product of Lorentz transformations obviously ends up being a product of unitary operators of each. So by the definition of how the unitary operator works, and we get the -1 comes outside the operator. So by 9.3, this is U of lambda acting on P. Okay, so what this means is that we now have our U of lambda, which is this right-hand side, which u of lambda of p, which is equivalent to the right-hand side. For arbitrary lambda, I should say. Okay, so this is where, it depends on whether the particle's massless or not, because the isometry group is different in each case. So if p squared, which is m squared, so if the one particle state we're talking about is bigger than 0 mass or equal to 0, then the isotropy group is different. So we consider each in turn. So let's first take the massive case. Okay, here we choose our p dot. It's going to be convenient for us to choose it to be on the mass shell of the particle. In other words, the particle, there is no momentum. So all of the eigenvalues of the 3 momentum will bring back 0. So, the isotropy group of this, of Lorentz transformations on this p dot mu are obviously ones that just rotate the spatial directions. So gp dot is SO3, since lambda p dot is p dot, restrict lambda to the form lambda r is 1, and then some zeros, and then we have this 3 by 3 matrix R, where R transposed R is the identity. Now, strictly speaking, we could have some reflections and things, but we're considering cases that are continuously connected to the identity. We'll see right at the end of the section how we deal with things like parity transformations, which are not continuously connected to the identity. Let's calculate the Casimirs now to see what labels the irreducible representation have. The Casimirs, remember, label the irreducible reps. So we have this Pauli-Lubyansky vector. So of course so this 4 vector. So let's consider W0 acting on our P dot. Well, this is, if you just substitute in for W0, you get epsilon 0 ijk P I M J K on P dot. Now, essentially, when P di, the eigenvalue of Pi on P dot is P dot I, which is a 0. So this brings back 0. If I consider the ith component, where I is 1, 2, or 3, I get epsilon I 0 jk P 0 m jk plus plus epsilon I j 0k P j m 0k acting on P dot. And so here, this is equal to minus m over 2. Okay, so epsilon I 0 jk is the same as epsilon I jk with a minus sign, where now I've brought the indices down with the Minkowski metrics. So we get an additional, the 3 Minkowski metrics in the spatial directions required to do that. So we get an additional minus sign. The m comes from the P0 acting on P dot. And we've got mijk, mjk, P dot. Okay, well, yeah. So this is which is minus m j I p dot. So strictly speaking, you should use commutators to try and get this p0 operator on the other side of the mjk's in order to bring back this eigenvalue here. But you'll see that the commutator is 0, so we can do that. If you look at the algebra of the Poincare group back in section 5. So we're now in a position to compute the Casimir, which we said before was W mu. And so we get minus m squared j squared acting on p dot. And we know these ji's are just SU2 generators, and so this gives us minus m squared j plus 1 acting on p dot. So in all, we've got two Casimirs, and they specify the irreducible representation. These are characterized by p squared is m squared from p mu, and by j, the total spin. So in other words, if we have an irreducible representation, then it's the mass and the total spin which labels the different, if they've got different labels, then they're different irreducible representations. Now, 9.5 that we wrote down tells us what our lambda in terms of p and lambda should be in order to transform, and this is L of lambda p to the minus 1, lambda L of p, and this is a Wigner rotation. And 9.6 implies that the unitary operator, corresponding to this Wigner rotation acting on p dot, gives us u of L lambda p to the minus 1, u of lambda acting on p. And this is 9.7. So for any rotation R, p dot is an eigenvector of p mu. So if we take u of lambda r acting on p dot, this is an eigenvector of p mu with eigenvalue proportional to p dot mu. And so it's a linear combination of all states in Vp dot. So this implies that Vp dot forms a representation space. Well, okay, so these are really SO3 representations. But because we're dealing with quantum states, remember, Bargmann theorem kicks in and we get the universal cover of SO3, which we showed before was SU2. I.e., they're labeled by, so we know about these representations, of course, labeled by J as a half, 1/2, 1, 3/2, etc. And the third component of the spin between minus J and plus J. So assuming that the set of all of our states, which correspond to P dot and J3, assuming that forms such a space, but which is also irreducible, which is irreducible. So that's our assumption. So in that case, we have that U of lambda R acting on P dot J and J3. Well, this is made up of the finite representations of SU2. So we sum over all of the third components. It states P dot J J3 prime. And we have some representation matrices of the rotation, and it's the J spin representation, and the row index is J3 prime and the column index is J3. So 9.8, where DJR is the spin J representation matrix of SU2. Okay, good. So 9.3 reads as PJJ3 is the unitary operator of L of P acting on P dot J3. It's 9.9. And this extends the previous definition of the basis of the group. So then 9.8 implies, well, we just substitute in for lambda r here, that so u of L of lambda p to the minus 1 times u of lambda acting on P J J3 is the sum over J3 prime of P dot J J3 prime DJ representation J3 prime J3. Okay, so this is equal to the right hand side here is equal to, from 9.9, this is equal to the sum over J prime lambda P J J3 prime. And now I'm going to put the fact that this representation, of course, is a function of P and lambda in explicitly, just to remind us. So the states P J J3, P squared is M squared. So this is the restriction, P squared is M squared is bigger than 0. Then provide a basis for the irrep space of SO 1, 3. At least the bit connected to the identity. You can see. So this extends to the full Poincare group sort of immediately. Since for translations, we have our translation operator, which is a function of A acting on P J J3. This is just e to the I P A mu P J J3. Okay, and so we interpret this as a single particle state. Because it translates in the way that we expect those to translate. Let's call it one particle state of mass J and spin, total spin J. Okay, good. So next time we're going to look at the massless representation case. As I said before, here the isometry group is different. It's not this case of three-dimensional rotation. So what we actually get is the Euclidean group in a plane perpendicular to the direction of the photon, if that's the massless particle that we're considering. So it introduces a bit more of a complication, but we will be able to get to the end and show how that new isometry group changes this discussion that we've just had, where we have full representations of SU2. What we get if we've got a kind of spin J particle, with the new isometry group, the massless case, we'll only get states, helicity states, which are either plus J or minus J, and all of the ones in between will be absent. So, for example, with a graviton, massless graviton, which has spin 2, the states that you get are only in the third direction, are only spin plus 2 or spin minus 2. You don't get the 0, 1, and minus 1 like you would normally with SU2 being the Lie algebra of the isometry group. Okay, good. This is the penultimate lecture that we're just finishing now. So the next lecture will be, sadly, our last one.